Right now, roughly 1,000 trillion photons are hitting every square centimeter of your exposed skin. Every second. You cannot feel any of them. They have no mass, they have no size. They do not exist in any particular place until the moment something absorbs them. And here is the part that made one of the greatest physicists of the 20th century argue about them for 30 years straight, until the day he died. If you set up an experiment to catch one behaving as a particle, it behaves as a particle. If you set up an experiment to catch it behaving as a wave, it behaves as a wave. If you try to catch it being both, the experiment breaks, not the equipment. The physics, this is light. The most familiar thing in your world, the thing that enters your eyes so you can watch this video. And after 120 years of quantum mechanics, the most precisely tested theory in the history of science, nobody can tell you what a photon actually is without contradicting a different experiment. The strange truth is not that photons are complicated. The strange truth is that they are simple, and nature still refuses to let us see the whole picture at once. It started with a fight. Isaac Newton versus Christian Huygens, two of the sharpest minds in 17th century Europe, and they could not agree on what light was made of. Newton said particles. He called them corpuscles, tiny discrete objects that traveled in straight lines, bounced off mirrors, and could be split into colors by a prism. His evidence was shadows. Light casts sharp edges. It does not bleed around corners the way sound does. It behaves like something small and hard being thrown across a room. Huygens said waves. His evidence was refraction. When light passes from air into glass, it bends. Waves bend when they cross a boundary between materials. Particles do not, at least not in the same predictable way. Huygens published his wave theory in 1690. Newton published his particle theory in 1704. For the next 100 years, Newton won. Not because his evidence was stronger, because his reputation was. The man had invented calculus and explained gravity. When he said light was a particle, people listened. Then, in 1801, Thomas Young did something that should have ended the argument permanently. He took sunlight, passed it through a narrow slit to create a coherent beam, and directed it toward two slits cut side by side in an opaque screen. On the wall behind, where two bright lines should have appeared if light were made of particles, Young instead saw something else entirely. Alternating bands of bright and dark, a striped pattern stretching across the wall. This is an interference pattern. It is the signature of waves. When two waves overlap, their peaks can align and double in height, creating bright bands. Or a peak can meet a trough and the two cancel, creating darkness. Only waves do this. If light were particles, each particle would pass through one slit or the other and pile up in two clusters behind the slits. Young saw bands, dozens of them, perfectly spaced. Light is a wave. Case closed. For exactly 104 years. In 1900, the German physicist Max Planck was wrestling with an embarrassingly simple problem. Heat something and it glows. A coal in a fireplace, a filament in a light bulb, a branding iron pulled from the flames, the surface of a star. The relationship between temperature and the color of light an object emits should have been straightforward to calculate using the physics of waves. It was not. Classical wave theory predicted that as you move toward shorter wavelengths, toward ultraviolet and beyond, the energy emitted should increase without limit. An object at any temperature above absolute zero should radiate infinite energy at short wavelengths. This was called the ultraviolet catastrophe. The math said a warm oven should kill you with gamma rays. Ovens do not kill people with gamma rays. The theory was catastrophically wrong. Planck found a fix, but the fix horrified him. If he assumed that energy was not emitted in a continuous stream, the way waves work, but instead in discrete packets, each packet sized to the frequency of the light, the equation matched reality. Each packet carried energy equal to the frequency multiplied by a constant. That constant, h, has a value of 6.626 times 10 to the negative 34 joule seconds. It is unimaginably small, but it is not zero. And because it is not zero, energy is not smooth. It comes in chunks. Planck did not believe his own discovery. He described it as a mathematical trick. He spent years trying to find the real explanation. He never found it, because there was no trick. Nature actually works that way. Then in 1905, Albert Einstein made it worse. He was studying something called the photoelectric effect. Shine light on a metal surface, and it knocks electrons loose. Heinrich Hertz had observed this in 1887, but the details were wrong, all of them. In every direction that classical wave physics predicted, here is a way to feel the strangeness yourself. Imagine shining a dim red light on a sheet of metal. Nothing happens, no electrons come off, increase the brightness, flood the room with red light. Still nothing, not a single electron. Now switch to a dim blue light, far dimmer than the red was. Electrons immediately. Think about that. A tsunami of red light cannot dislodge a single electron, but a trickle of blue light knocks them free instantly. If light were a wave, brightness should be what matters. More energy, more push, more electrons. But the experiment says the color, the frequency, is the only thing that determines whether an electron is released. Brightness only determines how many are released once the frequency threshold is crossed. Einstein's explanation, light does not arrive as a continuous wave. It arrives as individual packets. He called them light quanta. Each packet carries a specific amount of energy determined by its frequency. One packet, one electron. If the packet does not carry enough energy, no amount of packets at that frequency will compensate. 1,000,000 photons of red light cannot do what a single photon of blue light can. This was the birth of the photon. Though the word itself was not coined until 1926, when the American chemist Gilbert Lewis named it. Einstein's explanation earned him the Nobel Prize in Physics in 1921, not for relativity, not for E equals mc squared, for proving that light is made of particles. But Young's experiment still shows interference. Light still behaves as a wave. So which is it? This is where the story stops making sense, and it has not started making sense again since. The double-slit experiment has been repeated thousands of times since 1801, with photons, with electrons, with neutrons, with atoms, with molecules containing over 2,000 atoms. The result is always the same, and the result is always impossible. Send a beam of photons through two slits. An interference pattern appears on the detector. Waves expected. Now reduce the intensity until you are sending one photon at a time. A single photon enters the apparatus. It hits the detector screen. One dot, one particle, one location. Wait a moment. Send another photon, another dot, another location. No pattern visible, but keep sending them one at a time. Thousands of individual photons, each traveling through the apparatus alone, each landing as a single dot. Plot every dot. An interference pattern emerges. The same pattern that would appear if a wave had passed through both slits and interfered with itself. Pause on that for a second. A single photon traveling alone through the apparatus somehow produces a dot in a location consistent with wave interference from both slits simultaneously. There was nothing for it to interfere with. It was the only particle in the experiment. Yet it behaves as though it went through both slits at the same time, interfered with itself, and chose where to land based on the result. Now here is the part that made Einstein argue with Niels Bohr, from 1927 until Einstein's death in 1955. Place a detector at the slits. Measure which slit the photon passes through. The interference pattern vanishes. Every photon goes through one slit or the other. Particles, two clusters, no bands. Remove the detector, stop measuring, the interference pattern comes back. The act of looking changes the result. Not because the detector disturbs the photon physically. Experiments have been designed with increasingly subtle detection methods. The result is always the same. Any measurement that could determine which slit the photon traveled through, no matter how gentle, destroys the interference. In July 2025, a team at MIT performed the most precise version of this experiment ever conducted. They used ultra-cold atoms trapped in an optical lattice as the slits and measured individual photons scattering off them. The relationship was exact. The more precisely they determined a photon's path, the more the interference faded. It was not a technical limitation, it was a law of nature. The universe refuses to let you observe both properties at the same time. Measure the particle nature, and the wave nature disappears. Measure the wave nature, and the particle nature disappears. Every experiment ever conducted confirms this. No exception has ever been found. Why? Nobody knows. So, what is a photon? If it is not a wave and it is not a particle, what category does it belong to? None. No category that existed before the 20th century applies. The honest answer, the one most physicists will give if pressed, is that a photon is a quantum object. That is not a cop-out. It is a recognition that the universe contains things that do not map onto any intuition the human brain developed in 400,000 years of tracking rocks and predators and fruit. In quantum field theory, the mathematical framework that provides the most accurate description of nature ever constructed, a photon is an excitation of the electromagnetic field. The electromagnetic field exists everywhere. It fills all of space at all times, even in a perfect vacuum. When the field is in its lowest energy state, its ground state, there are no photons. When energy is added in a specific quantized amount, the field vibrates. That vibration, packaged into a discrete unit, is what we call a photon. It is not a ball, it is not a ripple, it is a disturbance in a field that pervades all of space. And the disturbance has properties that look like a particle when you detect it, and properties that look like a wave when you let it travel. Richard Feynman, who won the Nobel Prize in 1965 for developing quantum electrodynamics, the theory that describes how photons and electrons interact, said nobody understands quantum mechanics. He did not mean the mathematics is too hard. He meant the mathematics works with extraordinary precision, but the picture it paints has no equivalent in human experience. In Feynman's formulation, a photon does not take a path from A to B. It takes every possible path from A to B simultaneously. Each path contributes a probability amplitude. These amplitudes are complex numbers that can interfere with each other. The paths that reinforce produce high probability. The paths that cancel produce zero probability. The photon is most likely to be detected along the classical path, the straight line, because that is where the most paths reinforce each other. But every other path contributes. including paths where the photon travels backward in time, loops around the galaxy, and arrives at the detector from the wrong direction. These paths contribute tiny amplitudes that almost perfectly cancel, but not quite. And the calculation that accounts for all of them matches experimental results to better than 12 decimal places. No theory in the history of physics has been tested to that precision and survived. A photon moves at 299,792,458 meters per second. This is the speed of light. It is also the speed of causality, the speed at which any influence can travel through space-time. Nothing with mass can reach it. Anything without mass must travel at exactly that speed. Not approximately, exactly. There is no slower photon and no faster photon. Every photon in the universe, from the lowest frequency radio wave to the highest energy gamma ray, travels at precisely the same speed in a vacuum. A photon is born at the speed of light and dies at the speed of light. It cannot accelerate, it cannot brake, it does not exist at any speed other than c. This is not a property that can be turned off or adjusted. It is a consequence of having zero mass. Now here is the part that should keep you up at night. According to Einstein's special relativity, time slows down for objects moving fast. The faster you move, the slower your clock ticks relative to someone standing still. At the speed of light, the time dilation factor reaches infinity. A clock moving at the speed of light does not tick slowly. It stops. From the photon's perspective, if such a perspective could meaningfully exist, it does not experience time. Not a slowed version of time, not a stretched version of time, no time at all. The moment of emission and the moment of absorption are the same instant. A photon that left a galaxy 13 billion light years away, that traveled across the expanding universe for 13 billion years by your clock, experienced zero duration. In its frame, it was created and destroyed at the same moment. The 13 billion years were yours, not the photon's. Every photon that has ever existed was born and died in the same instant from its own frame of reference. The entire life of a photon, by its own experience, takes no time at all. Think about what that means for the photons hitting your skin right now. The ones from the sun left the solar surface 8 minutes and 20 seconds ago by your clock. But by the photon's clock, there was no journey. No 8 minutes, no 150 million kilometers of empty space. The photon was emitted by a hydrogen atom in the sun's photosphere and absorbed by a molecule in your skin, and from its perspective, those two events are the same event. The distance between the sun and your face from the photon's frame is zero. It is not that the photon traveled very fast across a large distance. It is that, for the photon, the distance does not exist. The photon also has zero rest mass, but carries real, measurable momentum and energy. The equation that connects them is E squared equals P squared C squared plus M squared C to the fourth. For a photon, M equals zero. So E equals PC, energy equals momentum times the speed of light. Despite having no mass, the photon pushes things. Solar sails work because sunlight exerts radiation pressure. The momentum transfer is tiny per photon, but real. NASA has tested solar sail propulsion. The Japanese spacecraft Ikaros deployed a solar sail in 2010 and successfully demonstrated photon-driven acceleration in deep space. Massless, timeless. And yet it carries energy, carries momentum, and mediates the electromagnetic force that holds together every atom in your body. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a paper designed to prove that quantum mechanics was incomplete. They described a thought experiment involving two particles created together in what is now called an entangled state. Measure a property of one particle and the corresponding property of the other is instantly determined, regardless of the distance between them. Einstein called it spooky action at a distance. He intended it as an insult. He was certain that the two particles simply carried hidden predetermined values from the moment they were created, the way two gloves packed in separate boxes would. Find a left glove in one box and you instantly know the other is a right glove. No spookiness required. In 1964, the Northern Irish physicist John Bell devised a mathematical inequality that could distinguish between Einstein's hidden variable explanation and genuine quantum entanglement. The test was elegant. Measure the properties of entangled photon pairs at different angles. If the photons carry hidden predetermined values, the statistical correlations between measurements at various angles obey a mathematical limit. If quantum mechanics is correct, the correlations exceed that limit. The math is precise, the prediction is specific, and the difference between the two possibilities is measurable. The experiments have been done over decades by multiple independent groups with photons, electrons, and atoms. The correlations violate Bell's inequality. Every time, in 2022, Alan Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for proving it beyond any reasonable experimental doubt. Einstein was wrong. The photon does not carry a hidden answer. The answer does not exist until the measurement creates it. And the partner photon, regardless of distance, correlates instantly. This does not allow faster-than-light communication. The individual outcomes are random. You cannot choose your result and therefore cannot encode a message. But the correlations between entangled photons are stronger than any local hidden variable theory can produce. The implication is precise and technical and has been stated carefully by physicists. The universe is not locally real. Either information is not limited by locality, or particles do not have definite properties before measurement, or both. And photons are the particles that proved it. Here is what you are made of: carbon, hydrogen, oxygen, nitrogen. These atoms are held together by chemical bonds. Every chemical bond is mediated by photons. The electromagnetic force carried by virtual photons exchanged between charged particles is what keeps your atoms configured as a person instead of a cloud of disconnected particles. Every nerve signal in your brain, every muscle contraction in your body, every chemical reaction that sustains your life runs on electromagnetic interactions, runs on photons. You exist because of something that has no mass, no volume, no experience of time, no definite location until measured, and no single coherent identity that any human language can describe. There are roughly 400 photons from the cosmic microwave background in every cubic centimeter of space, left over from 380,000 years after the Big Bang. They have been traveling for 13.8 billion years. They fill every room you have ever been in. They pass through your body continuously. The light from your screen is photons. The heat from your coffee is photons. The radio waves carrying this audio are photons at a different frequency. You have never once in your life been more than a few centimeters from trillions of them. And the strange truth is that the question, what is a photon, does not have an answer in any language the human mind currently speaks. We can describe its behavior. We can predict its behavior to 12 decimal places. We can build lasers, fiber optic cables, solar panels, quantum computers, and MRI machines using its properties. But we cannot say what it is. After 120 years, the most precisely tested theory in the history of science describes the photon perfectly and still cannot tell you what you are looking at when you see the light. That is the strange truth. Not that we do not know, but that we know everything about it except what it is. Subscribe to the channel and leave a like if you made it this far. Thank you for watching, and see you in the next video.